website. So, and we will not probably then use Zoom recording. Okay, so let's start the course. So I want to explain what this course is about. So let's take so it's kind of introduction. So let's take a system of polynomial equations in n variables. So we have some k polynomials in n variables. So I'm going to assume that this fi are polynomials with integer coefficients. And then, so having this, I can do the following. I can define, I can fix some a prime number, prime integer, and denote by n sub m. Consider the sequence of integers, which is the number of solutions to this system, right? So let's give a name to this. In a finite field. So f p to the m. So for every positive integer m, we had a sequence of integers, n1, n2, and so on, right? Very good. So, well, one thing to remember about this field is that it's not z mod p to the mz, right? It's different. So you can of course consider solutions in this ring, but it's completely different problem. So I want to understand the pattern, right? So here is the conjecture. So Weil's conjecture. Well, which is now a theorem. In fact, it's a theorem of Dwork. This conjecture works. Theorem. It shows the following, that if I form the following generating function for this sequence, so the generating function is going to be the following. I take sum of n sub m over m times the formal variable t to the power m. But that's not all. So I want to take, so this is summation is from m equal to 1 to infinity. It's infinite formal power series that starts with 0 constant term. So I can take its exponential, just formally, right? So I get a formal power series, right? So that's definition. So it's in Q double bracket C. And the conjecture says that this formal power series is actually rational. That is z of t is an element here, right? So, as you see, it's very general statement. It refers to any system of algebraic equations, any algebraic variety. So, okay. probably I have to use these two blackboards. So here is a remark. So it's this generating function looks a little bit strange. So if you so here is a remark. So let's take we can relate this generating function which with more with a kind of more familiar probably to everyone. Namely, we can take the z of t and consider the following new function: z prime of t. This is the derivative, the logarithmic derivative times t. So this is t t d over dt applied to logarithm of z of t. Okay. So now question to everyone. So what do you get? So z of t is given by this formula. So what do you get when you apply this operator? Which power series? Well, I don't think that you. Yes. So you have to differentiate this power series and then multiply by t. Yes. Very good. So that's what you get. So this sophisticated generated function is related to kind of more familiar one by this formula. And therefore, as a corollary, we see that this power series, again, sum over all m, is also rational. It's a corollary not of this, well, it's a corollary of Weil conjecture, right? So saying that z of t is rational is stronger than saying that this is rational. Because of course, if you have a rational function, this is the result of this, its logarithmic derivative is also rational, but not vice versa. So again, a question to everyone. So suppose I give you a sequence n sub m. When the generating function is rational?
So you have to have a linear, eventually have a linear recurrence relation.
Very good. Yeah. So you have to have a linear recurrence relation. So that means that, so roughly speaking, if you know first, well, everyone knows what a linear recurrence relation is, right? So it means that it's constant coefficients. So now here is a less familiar observation related to this generating function. So let's take so another remark. We can take suppose we have a sequence of complex numbers. So AI are complex numbers. And let's Then the claim is that the two conditions are equivalent, so we can form this sophisticated generated function, exponential of sum of a m over m to the power t to the m. And the claim is that this generating function is rational if and only if the following condition holds: there exist some complex numbers, alpha 1, alpha r, and beta 1, beta s, complex numbers, such that this sequence A sub m for every m, A sub m is equal to sum alpha I to the power m I equal 1 r minus sum of beta j j equal 1 s. So if you have a linear recurrence relation, then you can form what's called characteristic polynomial, right, of the linear recurrence relation. And if the characteristic polynomial has no multiple roots, then every solution to a linear recurrence relation is a linear combination of powers of its roots, right? So if you have a sequence, as we already see, if you have a sequence of complex numbers such that this power series is rational, then in particular this power series will be also rational, so it satisfies linear recurrence relation. So a priori we know that so A sub m must be a combination, well, at least if you don't have multiple roots, you have a combination of these guys with some coefficients. And the claim is that this stronger condition, rationality of this function, implies that all the coefficients are plus or negative 1. So, this is not entirely obvious, but and I will not prove it, I will not use it, except for one direction. So I will explain. Well, it's an easier part of this. So proof, I will explain that this condition implies this. So, right? So you see, if you have two sequences such that this generated function is rational, then it's also rational for the sum of the two sequences. So it suffices to prove it just for one, for a alpha to the power m. So so it's so this implication follows if we prove that exponential of sum of alpha to the power m t to the m over m greater than 1 is rational. That's our goal. And maybe someone can tell me what this rational function is.
It's 1 divided by sum of 1 minus alpha t.
So it's 1 over sum. So that's what I hear, alpha t. Right, this? Okay, like this. So I will, well, that's the answer. So the idea is to recognize here the Taylor expansion for the logarithm. Right? So and then you get the result. Very good. So that's the fundamental formula that we are going to use 1,002 times in this course. And this proves one implication in one direction. Okay? So, so I stated the conjecture, at least first conjecture. And, well, if you see a statement, how can you sort of judge whether it's deep, profound? Well, it must be general, and it must have must be non-trivial in special cases. And this is a very good example of such a statement. So in fact, this conjecture had some has precursors. So actually, the first result, well, in the case when the system, my system of polynomial equations is linear, so all polynomials of degree 1, then this is the trivial case. We are just computing the number of points on the affine space. So it's used to this. So quadratic equation is also not that, well, if you have one quadratic equation, so you're computing the number of points on a quadric, it's also not that difficult. It's essentially reduced to the linear case. But already when you have one equation of degree 3, it's already highly non-trivial. So the first example, which is due to Gauss, so Gauss looked at the following equation, y squared minus equal to, well, x cubed minus 1. So this is known as an affine elliptic curve, right? So we have to fix a prime number p and form this generating function. So, and I'm going to assume that p is not 2 or 3. It's this can be also considered to formulate the answer which works for all pi. To assume this, and then so what Gauss proved is that, and I hope that everyone will be able to prove it by himself or herself tomorrow, that this this generating function, which is called the Zeta Function, has the following form. It's 1 minus AP plus PC squared 1 minus PT. Okay, so it's a quadratic polynomial over this, and here, what is so here AP is equal to P minus N1, right? So that's relation between, so this is, recall that N1 is just the number of solutions to this equation, modulo P, right? So first statement is that if I know just one number, then from this formula I know all other numbers, solutions, the number of solutions in the finite field of P to the n elements. But in fact, Gauss computed this N1 explicitly. and I will formulate his result. So the answer, question? Okay, the answer will depend. So I will tell you now what AP is. So the answer depends on the remainder of P modulo 3. So in the easy case, when P is equal to 2 mod 3. So how do you solve this equation modulo P? So the idea is that so the multiplicative group of the field of P elements has P minus 1 elements. It's a cyclic group of P minus 1 elements. And raising to the pth power, to the third power, is an isomorphism from this group to it's an automorphism of this group, because P minus 1 is not divisible by 3. So that means that every element in this case is a cube modulo P. So I can take any y and then I can solve it for x. And the solution is unique because under this condition, again, because raising to the to third power is an automorphism, there is only one cube root of 1 in my field. Right? So basically, so what is the answer? How many solutions do we have? No, we can take any y, right? And then for y, yes. So if you plug in this formula, we get 0. So in this case, what's called the zeta function is just this. No. Now, I haven't yet explained this. Now, so in general, this is so if P is 3, then the answer is much more complicated. Sorry, if P is 1 modulo 3. So and I will explain, but you should be able to prove it by the end of the next lecture. So here is the answer. You take trace of pi. I need to tell you what pi is. So pi is a complex number, so pi is an element of the ring Z omega, where omega is primitive. Well, it's exponential of 2 pi I over 3. So it's cube root of 1. And this pi is almost uniquely characterized by the property that norm of pi, which is pi times pi conjugate, is equal to p. So the point is that when you so this is a unique factorization domain. And you can ask whether P, prime number P, remains prime in this ring. So that's equivalent to asking whether in modulo P you have a cube root of 1, right? Because this ring is a quotient of Z of omega is the quotient of I will explain this in a second. Right. So in order to understand whether P is a prime in this ring, you have to understand whether, so it's asking whether P is prime is well, P is prime in this ring if and only if the quotient of this ring modulo P is a field. In other words, it's equivalent to asking whether this polynomial is irreducible over Z mod PZ. And this happens exactly, so it's reducible if and only if, well, you have cube root of 1 in Fp. So which means that P is equal to 1 modulo 3. So if P is equal to 1 modulo 3, P is not prime in this ring, and therefore, well, it's you can, because it's unique factorization domain, you can factor it like this, right? So there are prime factors. One is conjugate to the other. So this factorization is almost unique. You can there are some finite number of units, 6 units here. So up to this, it's unique. And you can actually, Gauss tells you precisely which pi with this property you have to take. It must be equal to 2 mod 3, but okay, so I will not even write it down. We'll write it later. So and what is this? This is the twice real part of pi. Okay, that's trace. So that's the answer. To demystify this theorem of Gauss a little bit, let me I'll explain where this ring comes from. Well, as we are going to see, this first result, this kind of type of the formula for the zeta function is very general. It's something like this is true for any cubic equation, and even any equation, well, any curve. So for that matter. So, but the fact that you can actually compute this number solutions. So the general, well, for any cubic equation, we will see that once you know the number of solutions modulo P, you know the number of solutions in any finite field of characteristic P. But computing, yeah.
Yes, this beautiful deduction and always, if P would be a huge prime number, like a couple hundred digits long, then this pi is still hopeless to compute, right?
On the one hand, yes. But on the other hand, you can. This formula is very useful for proving results about zeta function of this curve, and I will explain what I will try to answer your question. Why I explain why this is useful later today. Mm-hmm. So that's a good question. So it doesn't seem kind of very explicit. You're absolutely right, but still it's useful.
In the first case, when x is equal to 0, you see that this is function that depends on p, which is completely not obvious. It is functional dependence on p, because you start with integer polynomial.
No, but I reduce modulo P. I look at solutions, the number of solutions. I'm not sure that I understand your remark, Volodya. Да.
И берешь разные пи, как бы твоя функция зависит от пи.
Да.
Сам факт, что ты можешь записать функцию как зависящую от пи, по-моему, это уже даже удивительный факт.
Ну да.
Это был вопрос номер 0.
Да. So maybe. Да. That's a very good. Yes, but you see, suppose I look, имеется в виду то, что зависимость от P, она очень простая. Вот, например, вот не было бы этого члена. Okay. So, and I will try to make this observation by Volodya more precise later today. So now I want to explain why this ring is relevant to the question, right? So although this formula of this type is very general, holds for, again, for any cubic equation, so this the computation of AP is specific to this particular type. And so what is special about this equation is that this curve, this elliptic curve, has non-trivial automorphisms. So if you take a general elliptic curve, it has only one, its group of automorphism is z mod to z. The only thing that you can do, you can take a, take an element, send an element to its inverse. Elliptic curve is a group. Or in terms of equations, you can send x to x and y to negative y. But here, you can also multiply x by cube root of 1. So now, a remark. So let's take remark. So consider the elliptic curve. So E inside P2, let's say our complex numbers, doesn't really matter, and it will be given by equation y squared z equal to x cubed minus z cubed, right? So I want a homogeneous equation. Then, so this is a curve. It has it's elliptic curve, and I recall that any elliptic curve is a group, right? So that means that endomorphism of this curve form a ring. So any map that takes the neutral element for the group structure, which is precisely the infinity point, right, which is not belongs to this affine curve, corresponds to point z equals 0. So any map from E to itself that takes in the point at infinity to itself is automatically a group homomorphism. And so if you take, this is a ring. Yeah, so this is a ring. It's not trivial, but it's not hard either. And the main point is that this endomorphism ring of my elliptic curve is precisely this. So it's easy to see. So at least it's easy to construct a map from this ring to the ring of endomorphisms. You just need to I have to tell you where omega goes, and omega goes to it takes y to y, x z to z, and it multiplies x by omega, right? So this gives me a map from this ring to the endomorphism ring. And so it's well known that endomorphism ring of any elliptic curve for complex numbers cannot be larger than this. Then it's what's called an order in the imaginary quadratic extension. So that's curves whose ring of endomorphisms is larger than z. You always have z, right? Are called curves with complex multiplication. So you can also multiply by some complex numbers. And later this by Hasse and Davenport generalized this computation of Gauss to the case of any elliptic curve with complex multiplications. So that's the fact that you have larger group of symmetries plays a crucial role. No such formulas are known for other curves. Okay. So so this conjecture was formulated for all curves by Artin. It was rationality was proven by Hasse in the case of elliptic curves, arbitrary elliptic curves. So Hasse proved a formula of this type for any cubic equation. But what was really kind of Weil's original insight is the relation, conjecture relation of this conjecture to algebraic topology. And that's what I'm going to explain. So Weil not only formulated this conjecture, he proposed a kind of a strategy for proving. Right? And strategy is very kind of simple and appealing. Simple and appealing. So let's take let's first formulate this in so let's introduce an algebraic variety or scheme. So I will take consider so I have a system of algebraic equations. Let's consider the spectrum, the affine scheme Fp x1 xn modulo f1 fk, right? So then, so this is an affine. This sits in the affine space over fp. Okay. The numbers, this n sub n that I defined, is precisely the number of points on this p to the m points on my scheme, right? By definition, because given a point on fp point on an affine scheme is the same as given a homomorphism from this ring to this field. And such a homomorphism is determined by where xi goes, subject to the relation. Okay, so now let's also consider. So this is a scheme over fp, but I want also to consider kind of a more geometric object. I want to consider a scheme over fp bar, and this is just x times spec fp bar. Right? So I can think of this. That's the quotient of polynomial algebra over fp bar modulo the same relations. So this is a scheme over fp bar, and so it comes together with a endomorphism, which I will call, which is called the Forbidden Syndomorphism. This scheme, right? Now, this endomorphism simply takes xi to every coordinate to its p-th power. So every coordinate to its p-th power, and in fact every polynomial with coefficients nfp to its p-th power, right? So because these polynomials have coefficients in fp, my f takes every fi to its p-th power, and therefore it takes this ideal to itself. So it's well-defined endomorphism of this ring, and therefore of the underlying scheme. Now, so the observation is that we can sort of, the main observation is that the numbers that we are interested in, well, the sets that we are interested in, is precisely the fixed point set of these endomorphisms. So what is it? It's f to the power m, right? So if you have a scheme and you have an endomorphism of a scheme, you can consider a closed subscheme fixed point subscheme, right? So let me kind of explain a little bit more what I mean here. So if you so this is a closed. Oh, sorry. So this is a closed subscheme here, which is in fact. So what is the equation for this closed subscheme? Well, the equation is the following. I write you many equations. So the equations is that xi to the pth power is equal to xi. So you take these equations and you add extra equations. That the pth power of xi is equal to xi. So as you see, it's all these equations together define a zero-dimensional reduced subscheme here, and its points correspond to this. So these are precisely solutions. So what can you say about an element in F? So the point is that Fp is characterized inside Fp bar as the set of points such that x to the pth power is equal to x. It's precisely the solutions to the equation. So what you have to remember here is that so f p to the m is equal to the number, the set of all alpha in Fp bar, such that alpha to the power p to the m is equal to alpha. And if you use this observation, you get immediately this result. So, okay, now we can sort of forget about varieties over finite field. We just have, a scheme. We have a more geometric object. We have a scheme over an algebraically closed field. We have an endomorphism of this scheme. And our goal is to find the number of fixed points. And we want to see how the number. So we are interested in fixed points not only on F, but of powers of F. And we want to see how these numbers depend on M. How this sequence of numbers depend. And so the idea was that there should be some, to use some, the idea was to kind of develop some technique coming from algebraic topology. So in algebraic topology, one can, if you have a topological, say, CW, smooth compact orientable manifold, and any its endomorphism, then the number of fixed points of this endomorphism can be computed as alternated sum of traces of this endomorphism acting on the homology of your manifold. And so there should be, the idea was that there should be some analogous construction here. So homology theory. Namely, to any x over Fp bar, to any scheme over algebraically closed field, one should be able to assign some homology groups and maybe even more relevant for immediate application. Homology with compact support. And so if X is this, if this scheme over an algebraically closed field comes, any endomorphism of this scheme should act on, it should be functorial, right? As usual homology theory, any F should act on homology. So this homology with compact support is usually in topology, it's not quite functorial with respect to all maps. It's functorial with respect to proper maps. Preimage of compact is compact. But Frobenius is finite. So, it's natural to assume that it should also act here. It's proper. And the main property is that we should have Lefschetz formula. And the Lefschetz formula will tell us that the number of fixed points F Fm, Fp bar, so the cardinality of this set can be computed as the sum of traces. So let me see. I want D here. So traces of F to the power M star, and it acts on homology with compact support in degree D of X Fp bar to itself. Right? So this is the analog of the Lefschetz formula. So here I should say that what kind of object this homology is. So these are some vector spaces, right? So vector spaces over some field. We don't really care what this field is. So we only want this field to have characteristic 0, because at the end our goal is to compute this number, which is an integer. If it were of characteristic p, then we could only compute homology the number of fixed points modulo p. And the observation is that once you have this theory like this, the conjecture follows immediately. Because then so let's see what we have here. So we are computing trace of an power of an operator acting on a finite dimensional vector space. What is the trace of an operator? It's sum of its eigenvalues. What is the eigenvalues of powers of this operator? It's just sum of powers of eigenvalues. So we immediately see that this is equal to the sum of alpha I to the power m minus beta j to the power m, where j, well, some finite sums. Okay, and this is I equal to 1. Right? So that's precisely this this form where where alpha I, beta j are eigenvalues.
But we still have to get rid of multiplicative, right? Because Lash's formula equals certain function.
Well, I mean, no, I don't have to get rid of any multiplicities. So if I have I count, I list here eigenvalues with multiplicities, right? So these are right. So every eigenvalue should appear here with its what's called algebraic multiplicity. I mean the multiplicity of the characteristic polynomial of the Frobenius, right? No. That's what I said. That for the Frobenius, the fixed point locus is discrete. Because it's discrete already it means that it's a reduced subscheme. There are no multiplicities. All the multiplicities are equal to 1. So basically what you do? So what is the explicit equation for what is x sub f? How you define it? Okay. So you define it as spectrum of a certain ring. And this ring is, you take fp bar, x1, x... What? Okay, yeah. So I will... let me write it here. So x fp bar f, I will just write this. This is spectrum of the following ring by definition. So you take fp bar of x1, xn, modulo the following ideal is generated by f1, fk as before, right? And now I want to so how we formulate the condition that it's fixed under f. For every function f, its pullback with respect to Frobenius should be equal to the function itself. So it suffices to check it for coordinates. So the equations are really xi to the pth power minus xi is equal to 0, right? That's the equations. That's how you. So if you want a more sophisticated. So here is a kind of more geometric definition. So let's consider the map from x to x times x, which is given by the graph of this Frobenius morphism. So in this, right? So the first coordinate is identity, the second coordinate is f. And here I have the diagonal. So what is by definition the fixed point subscheme? The fixed point subscheme is defined as a fiber product. Right? You look at points where the graph intersects the diagonal. And you do it kind of scheme theoretically. So it's, in principle, that could have some nilpotence. And this nilpotence are responsible for multiplicities that you may have. But here you don't have any, because if you just discard even these equations and just keep these equations, you get already finite discrete set. Uh-huh. So that's what I wanted to explain. So precisely. So this x f fp bar sits inside as a closed subskin in a finite space, fp bar, this is f. And already here, so if you discard these equations, just consider this. That's already discrete. Okay, I will not. Yes, yeah. Yeah. Okay, so let's see how it goes this time. Now, so that's the idea, and that's kind of the idea that we are going to follow in this course. So develop this, construct this homology theory, and prove the Lefschetz formula. But this is only one conjecture that I formulated. So the first Weil conjecture. I'm going now to explain for you statement of other conjectures, whose proof, well, the most difficult part was proven by Deligne, also relies on kind of ideas from algebraic topology, much more sophisticated than the Lefschetz formula. So we will kind of study algebraic topology over a finite field, over algebraic closure of a finite field in this course. So, okay, so that was an introduction. That's kind of, so it's 1/3 of what I plan to say today. So now let's start the course proper. So I want to, that's kind of next section. So I want to tell you what the zeta function of any scheme is. Function. That's going to be a generalization of what we just discussed. So let's take a scheme. Of finite type over Z. Right? You can think of a fine scheme, which is just a spectrum of a finitely generated ring. And scheme of finite type can be covered by finitely many affines with this property. So, so absolute value of x will stand for the set of closed points. Of x. Scheme theoretic points. So if I have a closed point, well, I have a local ring at this point. I have a maximal ideal. And I have the quotient of this local ring modulo the maximal ideal. And this quotient is called the residue field of my point. And now notation, the norm of a point is defined to be the number of elements in this residue field. Well, of course, I need to know that it's finite, and it follows from the following lemma. So if you have, if f is a field which is finitely generated a ring. Which means that it's a quotient of the polynomial algebra over Z, infinitely many variables. Then F is finite. And this statement is called Hilbert null. Well, it's equivalent. It's one of the formulation of Hilbert Nullstellensatz. Well, it's okay. So I will not prove it. And corollary is that the norm of X is finite. And now the main definition here, zeta function. So zeta function is well, it's going to be a function in complex variable S, defined as an infinite product over all closed points. And what you take product of, you take 1 over 1 minus norm of X to the power negative S. So here S is a complex number. So, well, of course, one has to, in order, when you write such a formula, one has to prove that it converges, at least for some S. So the result here is proof I explain, well, at least for I will explain it. I will give detailed proof for varieties over a finite field. That's maybe I'll for varieties over a finite field, and again, we'll give an idea in general. So here is the lemma. So the product converges absolutely and
estimate this, so we don't actually do this.
Yeah. Also good enough. This more precise estimate is really crucial. So the proof, is the original proof of Vadim, uses some analysis. And this kind of, that's a simplest example of the analysis doing. So, okay, so examples, well, so the name, of course, comes from, and the definition comes from another Riemann zeta function. So if you take zeta function of spec z, what are closed points of spec z? Primes. So you get so for overall primes 1 over p negative s, and this is sum 1 over n to the s, sum over all positive integers. That's the usual set. So another example. Okay. So let's assume that x is over fp, not even of p. Let's say fq. Fq is a power of p. Then so what do we have? So for every x in for every closed point, k of x is a well, it's a finite field, but it contains this one. So it contains a field, and therefore the norm of x, well, the number of elements here. So what can you say? Suppose that one finite field contains another. What can you say about their orders? Good. So that means that this is q to some power for some. And I will call this n degree of this. So every closed point, for every closed point, I will define its degree to be this number. So that means that what we have here, in the case of scales over a finite field, are powers of this number. So I can rewrite the zeta function in this case. That's going to be product gain over all x. 1 over 1 minus q to the negative s degree of x. Right? And now it suggests to make a kind of substitution here, introduce a new variable t, which is q to negative s. And then I will rewrite this using the new variable as product over all closed points one minus 1 over t to the degree of x. And now the claim and the claim is proof though it's very easy, I don't have time, so I will just formulate it and stop. So let's call this, I want to think of this as a function in T, and I will call it Z of X, T. And the claim is that Z of X, T is precisely the exponential of the sum that we had earlier. And M over N times T to the where N is the number of points on X over a field of Q to the M elements. Okay? So that's all I have for today. Thank you for listening. Questions?
Да, слушай, а та лемма, которую ты формулировал, ну вот точная оценка, она доказывается через проекцию на афинное пространство, да, и оценку слоев.
Да. So the lemma on convergence.
Ну ты ж будешь потом доказывать.
Да. Okay.